Hello everyone, I am Ashish Kumar Prasad. Today I am going to discuss Gauss elimination technique. The dependence on determinants is the necessity to develop this method because Cramer's rule use the determinant and calculation of determinant becomes a heavy task when we are going for the matrices of n by n where n is large. So this method doesn't uses the idea of determinant and it is helpful not only for obtaining the solutions but also for determining whether the system is solvable or your system is not solvable, and if it is solvable, whether your system has unique solution or it has infinite number of solutions. It is also helpful for finding the determinants in easier steps when you have a matrix of order n by n where n is large. Say you are going to calculate determinants of order 6 by 6 or 10 by 10. Then the method which I am going to discuss will become helpful here in order to calculate the determinant of higher orders, and at the same time we can find inverses and we can use it to determine whether your system is solvable or not, and if your system is solvable, whether it has a unique solution or it has infinite number of solutions. Basically, this method emerged from elimination technique. So I am going to discuss one problem with the help of elimination technique, and at the same time I will show how we are developing the method which I call Gauss elimination method. So let us start with one example. So my example is solve the system my first equation is x minus 2y plus 3z equal to 9 minus x plus 3y equal to minus 4 and 2x minus 5y plus 5z, and that is equal to 70. So what I will do, in the right hand side I am going to write the coefficients of xyz as well as the right hand side in the form of matrix which I call augmented matrix. So let us write the coefficient of x 1, coefficient of y in first equation is minus 2, coefficient of z is 3, the right hand side I am writing 9. Again we jump on to the second equation, coefficient of x minus 1, coefficient of y 3, z is absent, so I am writing its coefficient as 0, and the right hand side is minus 4. Next, I jump onto the third equation, coefficient of x2, y minus 5, coefficient of z 5, and right hand side 70. So all to all, I have deleted the variable names and equality sign, and I have written the numbers in the form of matrix. Now in elimination technique, what I will do, I will use the first equation to eliminate x from second and third equation. I want to eliminate x from second and third equation, and for this I will just do one thing. I will multiply the first equation by 1. See here, coefficient of x is -1 and it's negative. I am writing as 1. So I multiply 1 to first equation and I will add it to second equation. Or you can say in short that I am adding first and second equation, right? So first of all, when I perform this task, let us see what is happening. I am writing x minus plus 3z and that is equal to 9. Here x minus x is 0, so I don't write anything. Minus 2y plus 3y is y. I am writing y. 3z, here 0 is there, so 3z plus 0 is 3z, so I am writing 3z. And 9 minus 4, that I am writing as 5. Next, I want to eliminate x from the third equation. So I will write equation number 3. So for that, what is the coefficient of x? Coefficient of x is 2. So I will multiply minus 2 to first equation and I will add it to third equation. And with this you can see minus 2x plus 2x is 0. Minus 2 into minus 2, 4. 4y. Minus 5y is minus y. Then minus 2 into 3z, that is minus 6z, and plus 5z. So minus 6z plus 5z is minus z, and that is equal to 9 to the 18. Minus 18 plus 17 is minus 1. And I am writing the coefficients as well as the right hand side in the form of matrix. 1 minus 2, 3, 9. X is absent. I am writing 0. Y, its coefficient is 1. So I will write 1 here. And Z coefficient is 3, 5, 0, minus 1, minus 1, minus 1. So this is the first task. Next, I will concentrate my attention on the last couple of equations. And there are two equations and we have two variables y and z. So I will use the second last equation in order to eliminate y from the last equation. So what I will do, I will multiply the negative of the coefficient. Negative of minus 1 is 1, so I will multiply 1 to second equation and I will add it to third equation. So with this I am going to get x minus 2y plus 3z, that is equal to 9, and simply y minus y is 0, 3z minus z is 2z. So I am writing y plus 3z equal to 5, and here y minus y is 0, 3z minus z is 2z, and 5 minus 1 is 4. And I am writing the coefficients in the right hand side. 1 minus 2, 3, 9, 0, 1, 3, 5, 0, 0, 2, 4. And one more step I am doing here, and that step is multiplying the last equation by a number 1 by 2. And with this, I am going to get z. So see what I am going to get. I am going to get x minus 2y plus 3z, and that is equal to 9. Y plus 3z equal to 5. And here I am going to get, say, z equal to 2. So in this way, you can see I have obtained the value of z. Minus 1, 2, 3, 9, 0, 1, 3, 5, 0, 0, 1, 2. I have obtained z as my last equation. So I will use this value to obtain y for that, I will substitute the value of z in the second equation. So see, when I substitute the value of z in second equation, I will get y plus 3z, and the value of z here can be obtained from here. So 3 into 2, and that is equal to 5. So it gives me y plus 6 equal to 5. So y equal to 5 minus 6, that is minus 1. So I got my value of y. Now I will substitute the value of y and the value of z in first equation in order to get x. So I write x minus 2 y is minus 1 plus 3 z value is 2 and that is equal to 9. So x minus 2 into minus 1 is plus 2 plus 6 and that is equal to 9, and from this you can see I am getting x equal to 9 minus 8, that is 1. So I got my value. So with elimination I am clubbing the back substitution and we are going to get the answer, and this is called Gauss elimination method. So my solution is x equal to 1, y equal to minus 1 and z is equal to 2. So I am getting my solution here. And at the same time, I want to discuss how we can justify whether my solution is unique or it is infinite in number. And before that, I have one major question: how we can say whether my system is solvable, that is, my system is consistent, or my system is not solvable, or you can say inconsistent. So first of all, I want to mark the pivot. Pivot means first non-zero entry in every row. See, in first row, the first non-zero entry I am marking. In second row, the first non-zero entry I am marking. And in third row, the first non-zero entry I am marking. So now you can see here that in the last column, you can see I am highlighting it. In the last column, there is no pivot, and this indicates that the system is solvable, right? So I am writing here no pivot in last column, and this indicates that my system is consistent. My system is consistent. And if there is a pivot in last column, then I will say my system is inconsistent. See, pivot in last column indicates my system is inconsistent. And if it is inconsistent, I will stop the procedure because I know my system is not solvable, and I will stop my procedure at this end. Next question is, if the system is solvable, means if there is no pivot in the last column, as we are getting here. So in that case, what I will do, my next question is to determine whether the system has infinite number of solutions or the system has finite number of solutions. For that, I will first discard my last column, right? First of all, I will discard my last column. I will cut, right? And I will look into the remaining column. So this is my first column, this is my second column, and this is my third column. So I will look into the remaining column, right? So if you found that no pivot is in the last column, then you say the system is solvable and or it is consistent. System is consistent. Then we can proceed, and for next question about uniqueness, I will first discard the last column. I will discard the last column. And once I discard the last column, there may be two cases. There may be two cases that remaining all columns have pivots. Remaining all columns have pivots, or there is at least one column with missing pivot. Or second case is that there is at least one column with missing pivot. With missing pivot. So if remaining all columns have pivot, then we say that we have a unique solution. The system has unique solution. And if there is at least one column with missing pivot, then this indicates the existence of free variable, and in this case infinite number of solutions exist. So if there is a column with missing pivot, then infinite number of solutions exist. So but we have to be very careful that before going to establish the uniqueness, I have to discard the last column, right? You first discard the last column and then you check whether remaining all columns have pivot or there is at least one column with missing pivot. So if all columns have pivot, then it indicates the system has unique solution, and if there is a column with missing pivot, it indicates infinite number of solutions exist. So here we can see that remaining all three columns, after discarding the last, there are three columns left, and you can see the first column. If you check the first column, you have pivot. If you check the second column, you have pivot. And if you check the third column, you have pivot. So all columns have pivot. So this is the case of unique solution. And you can see you are going to get unique solution in this case. So in next class, I will discuss how missing pivot informs you that infinite number of solutions exist. And again, I will take one example and we will understand how pivot in the last column tells you that your system is inconsistent. Right? With these two examples, I will discuss some more insight of Gauss elimination technique, and I will try to develop Gauss-Jordan method from Gauss elimination technique. So thank you. See you in the next class. I request you to subscribe my channel and press bell icon so that every lecture will reach to you as soon as possible. Thank you.